In this explainer, we're going to break down what quantum computing actually is, where it stands today, and maybe most importantly, when we can realistically expect to see real-world solutions. Okay, let's get one thing straight right off the bat. This is probably the biggest misconception out there. Quantum computers are not just souped-up versions of your laptop. They're not going to make everything faster. Think of them less as a Swiss Army knife and more as a highly specialized surgical instrument, designed for a very specific, very tough set of problems. So, to really get why that is, we need to dive into the fundamental principles. What is it at their very core that makes these machines so fundamentally different from anything we've ever built before? It all starts with the most basic building block of information. In a classical computer, everything boils down to a bit, which can be a 0 or a 1, on or off. Simple. But a quantum computer, it uses something called a qubit. And this is where things get really wild. A qubit can be a 0, a 1, or it can be both at the exact same time. Now, this mind-bending ability of qubits is the key to everything. It all rests on three core principles from quantum mechanics: superposition, entanglement, and interference. You can think of these three as the engine that powers the whole machine. So let's take a look at each one. First up is superposition. This is exactly what we were just talking about. As long as you're not looking at it, a qubit exists in this weird, fuzzy state. It's a combination of all its possible values at once. It's only when you actually measure it that it's forced to, well, pick a side and collapse into a definite state, either a 0 or a 1. Next, we have entanglement. This is the one Einstein famously called spooky action at a distance. And it really is spooky. When two qubits are entangled, they're inextricably linked. If you measure one, you instantly know the state of the other one, even if it's on the other side of the universe. This bizarre connection is an incredibly powerful resource for computation. And the third piece of the puzzle is interference. This is where you cleverly use the wave-like nature of qubits to manipulate the probabilities of your final answer. Think of it like this. You set it up so that the paths leading to wrong answers cancel each other out, just like waves canceling each other out. At the same time, the paths leading to the right answer reinforce each other. It's like the computer is filtering out the noise to make the correct solution shine through. So here's the kicker. When you combine these three principles, superposition, entanglement, and interference, you unlock an absolutely massive amount of computational power. We're talking about solving certain types of problems in minutes that would take the world's most powerful supercomputers literally billions of years to crack. It's not just a little bit faster, it's an exponential leap. Which, of course, brings us to the next big question. What kinds of problems is this amazing specialized tool actually good for? And just as important, what is it not good for? Well, the range of potential game changers is huge. In cryptography, for example, Shor's algorithm could theoretically break much of the encryption we rely on today. For chemistry and materials science, you could perfectly simulate complex molecules to design new drugs or super-efficient batteries. And in the world of optimization, you could fine-tune things like global supply chains or financial models to a level we can barely even imagine. But, and this is a really big but, it's crucial to remember what they can't do. A quantum computer isn't going to make your web browser any faster. In fact, they're terrible at everyday tasks like sending an email, running a database query, or rendering graphics. For all that stuff, the classical computer in your phone or on your desk is and will continue to be the perfect tool for the job. So that begs the question, where are we right now, in 2026? The short answer is we're smack in the middle of what's called the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum, and those two words really tell the story. Noisy because the qubits we have today are incredibly fragile and prone to errors, and intermediate scale because while we have a decent number of them, it's nowhere near enough to tackle those huge world-changing problems we just talked about. Yeah, the technical challenges right now are just immense. We've got machines with anywhere from 50 to around 1,000 qubits, but like we said, they're very unstable. We don't have effective error correction working at scale yet. Oh, and these things have to be kept at temperatures colder than deep space, just fractions of a degree above absolute zero, which makes them incredibly complex and delicate. And believe me, the race to build a useful quantum computer is definitely on. You got the tech giants, IBM, Google, Microsoft, pouring billions into this.
Then you have more specialized players like IonQ and Quantinuum, who are taking different technological approaches. Everybody's got a slightly different strategy for trying to crack this incredibly tough nut.
So the reality check for today is this. What we're seeing is a ton of research and experimentation. Some companies are running early pilot projects, mostly just to get their feet wet and learn. But a widespread economic breakthrough, or a real quantum advantage that you can see and feel, we're still a long way off from that.
So, what does a realistic roadmap actually look like? When can we expect to see some tangible results from all this effort?
All right, in the near term, say between now and 2030, we're mostly going to see hybrid systems, where classical computers work alongside quantum ones. We might see some early advantages there for small-scale chemistry simulations. Looking out a bit further, maybe 2030 to 2040, that's when we could start seeing the first error-corrected machines that might deliver real breakthroughs in material science and pharma. But those huge society-changing disruptions, like breaking current cryptography, realistically, you're looking at 2040 or even later. And you have to take even that roadmap with a huge grain of salt. All of this depends on fundamental breakthroughs that haven't happened yet. We need robust error correction. We need to scale up to millions of stable qubits, not hundreds. And the whole hardware package has to become way more reliable and easier to manage. Okay, so let's pull all of this together and try to give a final assessment, cutting through all the hype that usually surrounds quantum computing. Here's how you can think about the current state of play. From a scientific perspective, this is absolutely revolutionary stuff. For the economy, in the short term, the potential is frankly overestimated. But long term, its impact on our digital security is critical and something we have to take very seriously. And as for productivity today, the impact is pretty much zero. Maybe the best analogy is this. Quantum computing today is where classical computing was back in the 1950s. We're talking about room-sized, incredibly expensive, and finicky experimental machines. Back then, nobody could have imagined that those behemoths would eventually lead to the smartphone in your pocket. The potential is absolutely massive, but we are right at the very, very beginning of the journey. So, what are the key takeaways here? First, quantum computing isn't going to change everything, but it will massively change a few very specific, very important fields. Second, this isn't an overnight revolution. It's a gradual evolution that will unfold over the next couple of decades. For companies and governments, the message is clear. Start preparing now. Start building up the expertise. And for you, as a private user, for now, it's still pretty much irrelevant to your daily life.